Welcome back. Welcome to lecture 2 of week 6 on probability theory with actuarial applications. Today we are going to build on the conceptual leap that we have taken in the last class of conditional expectation. And if you remember, we have defined conditional expectation and said that this conditional expectation will act as a random variable. And then we asked a question, what if I take expectation of this conditional expectation? That is what this law of total expectation is all about. So that is the context that we are going to discuss today. So first of all, let us understand why do we need this concept or average of averages. Okay. So what we have done in lecture 1, as I mentioned earlier, that was a big conceptual leap where we actually saw conditional expectation as my new random variable, which is a function of x. Now I am essentially asking for what is expected value of gx, right, and that basically means what do I infer about this when I am talking expected value of gx, because I have already eliminated y and now I have x. Okay. But the thing is, the structure of y is still inherent in this gx, and when I call upon this, what I get is expected value of y. Okay. That is an interesting property. So average of specific averages is just the overall average. Okay. So imagine this as we are building the tower, okay, and therefore this is called the tower property. Without losing the structure of y, we are actually computing with reference to x a new random variable, which will actually give you the properties associated with x, and when I take the expectation of that, what I get back is expected value of y, average, right. So this is very interesting and very appealing property. Let us try to visualize this property mathematically, or let us understand the mathematics behind this property of law of total expectation. So as usual, when you talk about the right hand side, it is expected value of the new random variable gx, and this new random variable, because I will apply the law of unconscious statistician for this expectation, I will only worry about this new random variable is nothing but gx, right. So I will only worry about distribution of x, that is fxx. So I will integrate over fxx dx, correct. So that is expected value of this. How will that fetch me the distribution of y and expected value of y, right? That is the trick, right. So now what we will do, we will unfold this gx into our expression. So it is integral from minus infinity to infinity, this is fine, fxx is also fine, but what is this? You have used some definition, right. So it is minus infinity to infinity y f of y given x, y given x, d of what did we integrate over? Y, right, and then we calculated this with fxx dx. Now it is just a matter of rearrangement. So I will push this dy outside and fx inside. So this is what is this? This is my expected value of y given x is equal to x. So if I rearrange these integrals without alternating any signs, what I get is integral, this integral is over x, this integral is over y, correct, y f of y given x, y given x, fx of x dy dx. But what is this product? Can I unfold this as well, f of y given x? Yes, I can do that, right. So let me do that here. So both integrals are intact. First one is x second one is y, this is y, f of x comma y, and this is y given x. So, it is nothing but f x of x dy dx. Okay. So, now you can get rid of this f x of x. Then what I got is integral over x is equal to minus infinity to infinity, integral over y is equal to minus infinity to infinity, y f of x comma y dy dx. Now, can I interchange these integrals? Yes, I can, because everything is finite. So, I can interchange these integrals. So, this interchange of integrals will take me y is equal to minus infinity to infinity, y into integral over x is equal to minus infinity to infinity, f of x comma y, and because I interchange, this will become dx, this will become dy. And what is integral x minus infinity to infinity f of x y dx? Remember our marginalization procedure. This will give me, so basically what I am saying is x equal to minus infinity to infinity f of x comma y dx. What will this give me? This will give me f y of y, right. This is what our marginal property description is. So, if I use that marginal property description, this becomes integral from minus infinity to infinity y f y of y dy. What is this? This is essentially expected value of y, right. So, what we have seen, we have actually proved this law of total expectation, where I started with the right hand side and I came down to the left hand side, right. So, this is the proof of law of total expectation. Let us visualize it step by step. First, we had this, then as I mentioned, this expected value of y given x is equal to x is integral. So, put it as an integral, that is what I did. Then first one is integral over x, and the integral within the brackets is integral over y. Okay. Then I have regrouped everything, which I have also done. Then we actually looked at this conditional PDF multiplied with this PDF, and we got joint PDF. So, we got joint PDF, then we swapped the integrals, we integrated with respect to x, I got the marginal of y, and once I got the marginal of y, I can see this is nothing but expected value of y. Okay. So, what we have actually done is the 2D version of the law of unconscious statistician, okay, to get the expected value of y. So, this is an interesting insight when we are dealing with expected value of y given some other random variable. So, you can actually split this expected value of y given x into layers of this random variable, which is determined by some function called gx, and then when you take expectation of that, what you will get back is expected value of y again. So, now we have done the required theory. Now, let us understand this, how it applies in practice. Okay. So, for that, let us take one same example that we have done earlier, which is auto claims and home claims, and we want to find expected value of y. Okay. So, in this context, it is very easy. So, when I want to calculate this expected value of y, the first thing that I need to look at is this marginal distribution, right, and this y is very simple, it is only 0 1 valued random variable. So, what matters to me is this. Okay. So, 1 into this probability will give me expected value of y. So, here everything is very easy, nothing, I actually do not require any calculation, but let us verify what this law of total expectation actually says about this. So, in this case what we need to do is expected value of y given various values of x, right. So, let us first take x is equal to 0. What is it? So, here notice the fact that this y is 0 1 valued random variable. So, what I need to understand is y given x is equal to 0. So, this is essentially probability of x equal to 0 and y equal to 1. Does y is, what is the probability of y equal to 0 matter to me? No, because it will be multiplied with 0, because I am talking about expected value of y. And then because I have to deal with this conditional distribution, I have to look at this marginal distribution of x, Pxx. So, that will be probability of x equal to 0. So, that gives me 0.1 by 0.7, done. Okay. Now, let me take expected value of y given x is equal to 1. What will that be? Again the same logic applies, because y is a 0 1 random variable, it is 0.08 divided by 0.028. For clarity I will write this is x is equal to 1, y is equal to 1 upon probability of x is equal to 1, and then if I substitute this, it is 0.08 upon 0.28, and this is the term that we derived in the last class also. And then finally the last value y given x is equal to 2, and then it is 0.01 and 0.02. So, this is essentially probability of x is equal to 2, y is equal to 1 upon probability of x is equal to 2. Okay. So, that is 0.01 upon 0.02. Okay. So, once I have done this, what I will do, I have this expected value of y given x. This is what I need to compute, right. So, that essentially means I will write these values, expected value of y given x is equal to 0, and multiply it with the weight associated with marginal of x. Okay. So, I will write 0.1 by 0.7, this is expected value of y given x is equal to 0 multiplied with probability of x is equal to 0, that is 0.7, plus same thing expected value of y given x is equal to 1. So, that gives me 0.08 by 0.28. What will it be multiplied with? It will be multiplied with 0.28, which is probability of x is equal to 1. And then when you look at the last value, it will be 0.01 by 0.02 multiplied with probability of x is equal to 2, which is 0.02. So, essentially all these things cancel off, and what I am summing over is simply 0.1 plus 0.08 plus 0.01 is 0.19. So, both answers match. However, the calculation with law of total expectation was significantly longer, right. So, this is the takeaway, but both of them give same correct answer. Okay. So, let us visualize these steps one by one. First, we can easily compute using marginals, that is what I did first. Then we actually computed law of total expectation, average of averages. We computed this, substituted it in the formulation, and we got the answer to be 0.19, right. Okay. Let us try to visualize this for a continuous version where we handled the distribution over triangle, and that was slightly terse distribution. So, how will you do that? First, you have to get the marginals. You can easily do that by taking integral from 0 to y half dx. So, why it is integral from 0 to y? Because you look at this thing, right. So, whenever I am integrating over x, it is trapped with y. So, that will give me this particular thing, and then you simply take expected value of y, you get the answer to be equal to 4 by 3. Usual calculus way, you are getting this marginal. You use LTE, we will use our old knowledge, which is expected value of y given x is equal to x is 2 plus x by x, and now I will derive this fxx, which is 2 minus x by 2, and then I will simply take this integral, and in this case it simplifies a lot, and this factor of 4 minus x square pops out, and you are simply integrating that factor, and you get both answers to be correct. Here this becomes slightly simpler than the earlier version, where it was very obvious when we were dealing with discrete that law of total expectation is not that computation friendly. Then why do we require this kind of complicated computation? So, that is where we will look at the models where this conditioning significantly helps, and that one such model is compound model. Okay. So, that is what we will look at now, and we will pose an important question: why law of total expectation if expectation of y is often easy to compute just by taking the marginals, correct? So, to answer that, let me give you one real time use case, which is the compound model, in particular a random sum. So, this is the workhorse for actuarial science. I have number of claims, I do not know what they will be, I know they will be discrete, and typically I model them using Poisson random variable. Okay. So, the number of claims are random and they are discrete and Poisson. However, their claim sizes are also random and they are continuous. Okay. So, one set is discrete, one set is continuous, and typically we model them using exponential distribution. So, now what we want to understand is these claim sizes are random and the number of claims are random, and what will contribute to the total loss of the portfolio. So, the total aggregate loss will be essentially the number of claims that are coming along with what claim sizes they are coming, and together if when I sum them, what is the total aggregate loss of that particular year. So, S is x1 x plus x2 plus so on up to xn, and this S is random sum of random variables. Okay. And typically if you want to find the distribution of this S without using the knowledge of conditional distributions, it is very terse, you basically cannot find it. Okay. However, if you use LTE, that is law of total expectation, this expected value of S becomes a quick tool, or it becomes very handy to calculate this expected value. Okay. So, how will you do that? Let us understand this and let us see how this conditioning tool helps. Okay. So, let us take the problem where expected value of S is what our goal is, not the entire distribution. Okay. Okay. So, how will you handle this? Expected value of S is expected value of x1, x2 and xn. The problem over here is this n is a random variable. If this n is a fixed number, we have our tool which is convolution that can help us in solving this problem, right. So, that is what we will use now. So, I want to tame this random n. How will I tame this? So, what I will do is I will consider, if I want to compute expected value of S, okay, what is the other factor? N is the other factor, right. So, I will ask a question, expected value of S given N, right. What I am doing? I am using law of total expectation. Tower, I am building a tower. So, what I am doing here is I am actually fixing this N, right. So now I will take this insider information, which is expected value of S given n. Okay. Now I will ask a question, what is expected value of S given n is equal to small n? Can I answer that? Yes, I can, right. So this is what this will be. It will be expected value of x1 plus x2 and so on, because capital N is small n, is going to be expected value of xn, correct. What do I need is n is independent of xi's. If it is so, I will get this, but then this is nothing but summation over I equal to 1 to n expected value of xi's. Assume that these xi's are IID. Xi's are IID exponential, let us say with parameter lambda. So if I assume that, then what will happen? Then do I know this? Yes, I do know this, right. Okay. Now comes the real kicker. So I have this kind of thing, right. So it is basically, if all of them are IID, this becomes n times expected value of x. Let us not put exponential lambda, IID setup is enough for me right now. So n times expected value of x. Now I will apply this. This insider is nothing but n times expected value of x. I want to take expectation. This expectation is with respect to what? It is with respect to n, right. So, let me write it here. It is with respect to n. So I will take that expectation. Now I am asking, what is expected value of s? So I have a primary answer, which is summation over, because these are the number of claims, n will vary from 0 to infinity, expected value of S given n is equal to n into probability of capital N is equal to small n, correct. And now I know this, this is n times expected value of x. So this is n times expected value of x multiplied with probability of n is equal to n. And now you see the beauty, n is equal to 0 to infinity, expected value of x is just another constant. So I will push it out. What is this sum then? N times probability of n is equal to n, this is actually expected value of n, isn't it? So what I proved? I proved this particular formula, expected value of s is nothing but expected value of n into expected value of x. This is a wonderful result. So if I have been given a random sum and asked what is the expected value of this random sum, the answer is very simple. You give me the summing variable n, I will calculate expected value of that, and you give me the underlying distribution or severity of the claim variable, I will calculate expectation of that, and I will take product of it, and that is all. I know the value of expected value of s, right. So let us let us revise the step by step solution to this, which is, first thing that we did is, we essentially took expected value of s given n is equal to n, which is what we are doing, conditioning on n. Then we assumed xi's are IID independent of n. So this expected value of s given n is equal to n became sum of expected values of n random variables which have same mean. Okay. So that mean we denoted with expected value of x and multiplied with n. Okay. So in particular, if xi's have mean mu, you just write expected value of x is mu, and the answer of expected value of s given n is equal to n is n times mu. Okay. So this is done. Then view this particular thing, expected value of s given n, as a random variable, which is your deterministic function gn or n mu, and then you take expectation of that. That is what I did, and then n mu is mu times expected value of n, that is what we proved, right. So finally we have the formula expected value of s is equal to expected value of n into expected value of x. Let us try to apply this to one more compound model. So, this is called compound model drill. The insurer company has claim frequency of n which follows Poisson with parameter lambda equal to 100, and the severity of the claim, which essentially means the claim size of the claim, has mean 500. Okay. What is the expected total loss for each year? Okay. So, you have been given expected value of x equal to 500, n follows Poisson lambda. So, you know what is the expected value of n, it is going to be 100 and this is 500. So, what will be the total loss of the company? It is just a 5-second computation. 100 into 500, 50,000 is the total loss that is expected, right. So, this is the most foundational treatment that actuarial people do. If you are given a compound distribution, how to compute the expectation. Okay. So, we have done significant work, we have learned the random sum today, and we know how to handle compound models using this tower property that we discussed, its law of total expectation, right. So, let us summarize what we have done so far. So, it is the average of averages rule, where expected value of y given x is actually g of x, but when you take expectation of it, you will reveal the average information of y, that is the beauty. So, in studying this, what we have actually gained is we conceptually understood the law of total expectation, and this particular thing will be significantly helpful for computing random sums. Okay. So, the shortcut for random sums is, if I want to compute this expected value of s, it is going to be expected value of the summing variable into expected value of the summed variable. Okay. So, what is coming next? Now, are we happy only with averages of s, or we want to tame its variance also? If yes, we want to tame its variance, because that is naturally associated with risk of the model, risk of the loss distribution, which insurer must be worried about. So, we need to learn the next law, which is called law of total variance. This is next conceptual leap that we will take in this course. Thank you. Bye.